So I'll take an example. We'll go through linear regression first, then we'll go through a normal neural network. So say I'm giving you this problem. You have 2 fish, 1 chips, and 1 tomato sauce, and I say it costs $12. Can you figure out how much a fish, a chip, and a sauce cost individually? How would you go about doing this, for example? Any ideas? So you're basically trying to figure out the price of each, how much does 1 fish cost, for example? Any idea how you could do it? You could write a mathematical equation. What do you think the mathematical equation will look like? Any? Sorry, Mark?
2x plus y plus z equals 12?
Yeah. So you can create this equation, y equals m1 times x1 times m2 times x2 times m3 times x3, where x is the number of fish, m is the price of the fish, and then y is the total amount you get at the end. So, so I give you not just one example, but this whole data set of things. And the goal is for you to create an algorithm that is able to detect how much each of those would cost, basically. So you can write it as y equals m1 x1 plus m2 x2 plus m3 x3, or writing it a bit concisely, you can say that it's all the w times x's summed up would give you the y. And this is basically linear regression. Who's heard of linear regression before? Okay, so and then based on the data, so you get 2, and then you put with neural nets, you basically make the goal of the neural net is basically to find the w's given the x's and the y's, the outputs and the inputs. So these w's are the numbers you will change in order to create this function. So you start with initially guesses about what these numbers could be, and then so you can say maybe initially I thought a fish was $3, a chip was $10, and a sauce was $7. Then if I calculate it based on the formula, it'll be $27. But I said the actual cost was $12. So that difference between the $27 and the $12 is the loss or the error. And there are different error functions, obviously. The difference, you can take the difference between the 27 and 12, and that'll be the mean absolute error. You can also take the squared, because the mean, if you just minus this by this, you'll get negative numbers. So to counteract that, you can use the mean squared error. Is basically one that's quite often used for regression problems, where you get the actual and the predicted, and what you do, and then how do you figure out? How do you basically figure out once you know this is wrong and you know how much it's wrong by, you can figure out how much of this to change, and how do you think you'll figure that out? So we use a thing called gradient descent in neural nets. So the basic idea is you would plot all these errors against the weight of each of these, so against each of these weights, and you take a step in the direction of the steepest gradient. So you can think of it like you have, so these errors you can plot for each, so this error you can plot for each input data point. And if you plot the data for each input, you'll get this, this field of errors. And then for each W, how that error changes as you wiggle that, that number. For example, if you wiggle the W here, how the error changes. So you basically try to wiggle the errors. This is just to give you an intuition. And then you change the weight in the direction that the error will decrease the most by. And then you do it by this algorithm called the backpropagation algorithm. I won't be able to explain it in the time we have today, but it's basically, who knows about the chain rule in calculus statistics? So it's basically the chain rule applied consecutively multiple times, but I'll leave that for you to go and check out some videos or something to read about. But basically, you take the gradient, you take the old gradient, which was the old W, and you multiply, you get the gradient, which is the direction that the error changes the most by, and then you multiply it by this learning rate. So the learning rate is basically determines how much to change that W. So the learning rate can be, it's a number you sort of have to play around with. So if you set the learning rate too low, the amount of time it takes for you to reach the bottom it'll take a long time. And if you set it too high, it will never reach the bottom. And basically your goal is to reach the bottom of this, to get the least error for your model. Actually, there's probably a better visualization of this. So if you've got, this is the step size. So if you've got a really low step size, don't worry about the momentum just yet. If you've got a really low learning rate, then it'll take a lot of time to reach the optimum. And if you've got a really high learning rate, it'll just go a bunch of places and will become really unstable. So that's learning rate. So this is basically the most simple way to update the weights, but there are more complicated ways. For example, you can think of it, how fast you're going can determine how there are people writing research papers about these different algorithms that perform differently. So what we talked about before was the SGD, or stochastic gradient descent. But there are other models. One that's quite commonly used is called ADAM, which we will use in the models today. But I said this is linear regression. So what is a neuron or a neural network? It's basically the same thing, but there's a nonlinear activation function added to the end of it. So you still have the x1 times w1 plus x2 times w2 times plus x3 times w3. And then you pass it through this nonlinear activation function. And this nonlinear activation function, you have a few options to select it from. So you have The most common one is the sigmoid activation function. So what comes out from here, this arrow here, would be the x here. So the output would basically be, for the sigmoid function, it's a function that goes from 0 to 1. So it converts whatever the number is into a number between 0 and 1, basically. And the rectified linear unit basically gets rid of all the negative numbers. Traditionally, the sigmoid activation function was used, but more recently, ReLU has been the one that's been performing well. It's just things for you to sort of, based on what other people are doing, ReLU seems to be performing quite well. So this is basically Neuron. You basically have a bunch of inputs. You have a bunch of parameters and an output. And you can see how it sort of corresponds to an actual neuron if you squint hard enough. So removing you can see, if you represent the neuron as this circle, a neural network is basically a collection of these neurons, and they come in all shapes and sizes. And if you noticed before, a neuron can only deal with numbers because we're doing mathematical calculations. So you might be wondering how we deal with images, or in the case of natural language processing, words. And the basic thing is you still need to convert them to numbers. And for the case of images, you can see that if you'll be able to convert this 8 into a bunch of numbers where the higher the value of the number means the darker the pixel is. The training data is like if you're going to an exam, if you can think of the training set as your practice exams. Well, actually, you basically, the model trains on the training data. And then on the validation data, you can think of it as the practice exam. And the testing data, you can think of it as the final exam. So the training data, so once you've got a data set, you normally split it into the training set, the validation set, and the test set. Usually like a 70-20-10 split or something like that. So 70% of the data will be training. So in the training set, this is the data that the model uses to train the model. And then the model doesn't see the validation set and the test set. After we train the model on the training set, we look at its performance on the validation set and see if it's doing good. And if it's not doing good, we can change the training set, change the model, do whatever we want, and test again on the validation set. And the testing set shouldn't be used right until the end, until we've finalized what model we are going to be using. So you'll be training on the test set. You'll be doing a few iterations between the training and validation set, and then you will use the test set at the last point in time before you, just to make sure that the model is still doing well. What is overfitting? So underfitting is basically when you create a model that is it's too simple. So for example, if we have these data points and we want to draw a line between the two classes, you'll have to if you just draw a line, it's not quite good. Ideally, we want something that is not overfit either. So what's happening here, why the validation loss is increasing is because it's actually trying to fit the noise in the data. And we're getting a line that is too complicated. And that doesn't actually, because we didn't give the model the validation data, it's actually overfitting. So it's not doing so well in the actual, in real life, it won't do well, basically. So ideally, you want to stop the training before the validation error starts increasing.